Welcome everyone to my talk with the title Automated Public Road Testing Based on Digital Twins. Well, my name is Patrick Luley. I'm with JOANNEUM Research and I'm responsible for the coordination of any research in the field of automated driving in our institute. Well, first of all, thanks to the organizers for this amazing conference. It's a pleasure for me, of course, to be part of it. So let's start. Well, first, some words about our research organization for applied science. We are a non-profit. Our headquarters in Graz, we're owned by federal states, and yeah, we are there since 32 years now, so quite a traditional company. And we are the second largest in Austria, and we have quite a big institute on ICT, which is the biggest institute of ours, and that's where I'm from as well. And in this institute, we started actually 40 years ago to work a lot with sensors, doing signal processing, doing data fusion, making applications on this sensor for industry. And well, 4 years ago, we thought, hey, all those competences are really relevant for the new field of automated driving. Well, and so we decided, let's make or found a research lab for automated driving. Yeah, and we did this in 2017. And well, it's not about developing automated vehicles or driving functions. No, it's about testing and validation of automated vehicles, and also with a certain approach of us. So we do the testing based on reference maps and based on reference sensor platforms to collect data, reference data we can compare with vehicle data at the end. And therefore, of course, you need a lot of software for evaluation. So this is our focus. And well, we thought, we want to put this in practice as well. We need some feedback from the industry. We want to apply our technology continuously and improve it. And so we decided to found, together with our partners, the first Austrian brewing region for automated driving with the name ALP.Lab. It's a kind of innovation lab. It's providing infrastructure and services for doing tests on public roads and also on proving grounds. Well, here you can see also the partners involved. So the industry partners are AVL and Magna, and the scientific partners, it's us, JOANNEUM Research, and also the Virtual Vehicle Research Center and the Technical University of Graz. Well, so and what you see here is the vision of our lab, or it's the map from the province of Styria, where we are located, and the red lines is the highway network where we want to do public road testing. And in the blue area, which is the province of Styria, it's already 400 kilometers of highways, and there is also a plan to connect our friends in Hungary at Salazone and then go back to Slovenia, Maribor, and up again to Austria, Graz, so to have this circle for testing with cross-border situations as well. So in JOANNEUM Research, we are now responsible for reproducing those reference maps and keeping them up to date. First, we talked about the requirements, or defined the requirements for those maps we need within ALP.Lab. And okay, there are qualitative requirements like 100% completeness, of course, of all the map features, and they have to be 100% correct because we want to use them as a source of static ground truth. And according to the accuracy, we wanted minimum plus minus 5 centimeter absolute positioning accuracy in world coordinates. And the features we want to include is, of course, the road geometry, so the slope and elevation, the chamber, the whole elevation profile, of course, of the road, and the road topology is very important, of course. Then we have road markings, we have traffic signs, and also all the constructions on the road or even on the side of the roads, like noise barriers, jersey barriers, guardrails. Those things are very interesting when it comes to sensor simulation, by the way. And as we are a research organization, we have also a scientific goal, and this is we want to produce this Ultra HD maps, we call them Ultra HD maps, in an automated workflow to make it in a scalable process which is cost and time efficient to keep it up to date. Well, and here is our process. We start in the left upper corner with this image of our mobile mapping system. This is a survey-grade sensor system with two laser scanners and several cameras, high-resolution cameras, to produce a very dense and very accurate point cloud. So this is not comparable to technology you have in ADAS vehicles. This is survey-grade technology. And well, after processing, you end up with this point cloud data. And then the first thing we do to be GDPR compliant, of course, is to do the anonymization. We do this automatically. Again, we detect number plates and faces, and we upload already data before the data is used in the lab already. The next thing is that we use our AI detectors to recognize all the relevant infrastructure on the road and do the automatic labeling within our digital twin. From this, next, we can deduce just the vector information to produce the maps needed for road testing. And at the end, you can use this data to go back to simulation and produce a difficult scenarios based on the real Ultra HD maps we produced. Well, here I can show you some examples how we do mobile mapping in practice. On the right side, you see an image when we did mobile mapping in the Sala zone in the very early phase, during the construction phase. And on the left side, this is very interesting. You see how we do mobile mapping on Austrian highways. We have a cooperation with the road operators, and they have two cars behind us holding back the traffic. And this is very important to get very clean data, because so we can avoid that anyone is overtaking us. And so we have no occlusions in our data from overtaking cars and get nearly perfect data. So this now is the point cloud data we are producing, which is very accurate, very dense, but I think all of you have seen a lot of point clouds in the past, so let's go on to the next slide. Go on. Here are examples of our detectors which we developed in cooperation with the Technical University of Graz. On the left side, you see that we are recognizing the road markings. In the middle, we are recognizing the traffic signs. And on the right side, what you maybe see not that often is recognition of the noise barriers, actually, yes. And we are not only detecting them, we are also doing the georeferencing of this data. So we are deducing all the boundaries of each lane marking on the ground or boundaries of traffic signs and have this in geo world coordinates with ±2 centimeters accuracy. And then we put this in our map. So on the left side, you see the mobile mapping data. This is the point cloud, the textured one here. And on the right side, you see what we end up after using our detectors. So we get all the map features we need for our Ultra HD maps. Well, and here I can show you an example of a highway intersection next to Graz. So this is a web-based analytics fluid which we developed on our own. So we're just zooming in now to this point cloud data, and you see we have already overlaid the Ultra HD map, and which is fitting correctly, of course, to our data. We have lane markings, we have all these arrows on the ground, and yeah, you can zoom in, you can go around, you can measure, you can see any detail. Also, of course, of here, where you see the rail guards, that's very interesting. Well, so next I want to show you how we are using this Ultra HD maps or digital twin actually for the testing, the road testing of automated vehicles. Well, this is a very basic figure I want to show you here. Our approach to do this is, okay, we have collected the vehicle data, the blue box, during the test drive, and we want to compare this data to what was actually there during the test drive. We talk about ground truth data. And once you have those two sources, you can compare it, you can do the ADAS-AD performance evaluation, and you have your KPIs, your assessments you want to do with this data. Well, now the question is, where do you get this ground truth data from? So, I start on the left side. What we've seen before about the Ultra HD maps. So this is kind of, we talk about static ground truth. It's what is really there, but is not moving. It's a static ground truth. It's all in the map, all the things in the map. Secondly, we need dynamic ground truth. So all the vehicles are moving around our ego vehicle. And how can we collect this data? First approach is, we have a reference sensor box, which was developed on our own. You can put on the roof of the vehicle with kind of survey grade or really good survey, great sensor quality to survey the environment. And in the post-processing phase, we can do the processing of the data to find out all the objects around you. And secondly, we have another source on our highways in the frame of ALP.Lab. We have also infrastructure sensors like radar, laser scanners, camera, which are watching all the vehicles on the road and classifying them, and we know the trajectories, of course, of them, and this is also used for dynamic ground truth data. Well, here is also pictures of our reference sensor platform with a dynamic ground truth platform. We include LiDAR, IMU, radar, camera sensors. JOANNEUM Research is putting this all together, integrating the sensors, doing the calibration, the synchronization, the operation, all of this, yeah. And then our partner, Technical University Graz, is supporting us with the environmental perception algorithms. Well, what you see here is another analytics viewer of us, web-based, so you can zoom in, and there you can already see a fusion of static ground truth data and dynamic ground truth data. This is very interesting. So after your test drive, you're back in the lab, and then you can see exactly what we see here. You have a red line, it's the trajectory of the ego vehicle. The blue dot is the position of the vehicle, and for each position of this ego vehicle, you can see all the cars around with these boundary boxes you can see here. And this is amazing what you can do with it, because this is a fused ground truth data, and now you can compare what has the car seen with what we have here in our ground truth analytics viewer. Well, and here are just some examples. On the left side, we do automatically in a scalable software process, we do a comparison. What is the vehicle seen and what is the ground truth data when it comes to perception? So have you detected all the cars around you, classified them right, was the position of them right, and so on. And in the middle you see, it is very interesting. I hope you can see the yellow lines. This is from a mobile eye camera, the lane detections and the lane predictions from the mobile eye camera, and you can put it on top of the UHDmap, and then you can calculate automatically your KPIs, how good it was fitting to the real lane borders. On the right side, easy example, it's lane centering, but you can automatically calculate over thousands of test kilometers how was the performance of your lane keeping or lane centering in centimeter accuracy. Well, finally, after all this road testing, I also want to show you that you can use Ultra HD maps for simulation, of course, as well. Here are some examples. So when you have these vector maps from us, you can go back to simulation programs like here IPG Carmaker, which has its software libraries with 3D objects, and then those objects are put exactly in the right position and the right scale, and it produces this 3D visualization, which is very close to the real environment. So every painting on the road is exactly the same like on the real roads. And then you can run, of course, these simulations you want to, very realistic simulations in that case. Well, what you can here is another use case. So you can use our Ultra HD maps or even the digital twins. This, what you see here, is even more detailed. So we have really 3D reconstructed environment, and you can put this, for example, to driving simulators. You have a very realistic experience. This, for example, we see here is a proving ground from the company ALP. Very impressive. This is the driving simulator from the Technical University of Graz. So, and finally, I want to show you this. So this is what we are actually working on, is sensor simulation. That's the use case where you need really accurate, really dense 3D reconstructions, because you work with ray tracing methodologies, and you need to know the shapes of all the objects and the materials and the textures to calculate the reflections, the scattering, or the absorptions of signals. And here on the left side, this is on the right side now. What we see here, this is a radar simulation. So the highly reflective things like metal guardrails are really seen here in the simulation. And now it stops at this overhead construction, I think. Yeah, and on the other hand side, we have a LiDAR simulation running in the same environment in our digital twin. And well, we were able to reproduce in simulation the same results like in real test drives, which was amazing. Yeah, a lot of potential here. So this was my final slide. I would like to say thank you very much for your attention, and I'm really looking forward to our discussions during the panel afterwards. Okay, goodbye, everyone. See you.